See? बच्चे आ गए वेट करो या आवाज आ रही ना Is it working now? Is it working? Is it working?
Hello.
Hello. Hello. Hello. Hello. Hello. इसका बैटरी कभी कभी इशू होता है. Hello.
Hello. Hello.
Hello. Hello. Okay. Good afternoon, everyone. Good afternoon, everyone. Okay, so today we are going live on YouTube, and I'll take class on YouTube. And in last class, actually we had in vectors we have to complete few topics, means a few examples. So as this class is live, so I am starting unit and dimension, and in next class I'll discuss some problem on vectors when we will on our portal. Okay, so today I am starting unit and dimensions. How many of you are there? Okay, if you have joined, just write something, okay, and I'll start after that. Okay, Varshini. So today's lecture is all about the physical quantity and unit and dimension. So in unit and dimension, we are going to study about the physical quantity, how we measure it, and how they are related to each other. Okay, and it's a very fundamental topic of physics. So it's the first topic of the physics. So let's start with the unit and dimension. So the first topic of unit and dimension is physical quantity that we are going to measure. So let's start with physical quantity. So what is physical quantity? Physical quantity is something that we measure in physics. Whenever you have any expression in anything, you just measure something, and using physical quantity we can describe laws of physics, and we measure actually physical quantities are measured. Physical quantities are actually measured. So let's see, and what are the specific point about the physical quantity is that we get three properties of, or three type of physical quantity in physics. First one is that which has only numerical values. Actually these are ratios. For example, just take the refractive index, this one. You must have studied in 10 that refractive index, this we represent using mu, is speed of light vacuum. Okay, let's see, it's a vacuum. Upon speed of light in medium, speed of light in medium. Okay, so we can see here this refractive index is ratio of two speeds, one speed in vacuum and another in medium. So speed by speed is refractive index is just ratio of speed. So you have only numerical value, you won't have any unit here. Now the second one is magnitude only. We have covered this, we say it a scalar. So its example is that mass, charge, this you can also write speed. Speed is also a scalar quantity, and distance. These are scalar quantity which have only magnitude, not direction. The last one is the physical quantity which is known as vector. So vectors have magnitude as well as direction. So we in last chapter we have studied about the vectors, and the examples are displacement, torque, velocity, acceleration, force, momentum. These all are vectors. Okay, so this is all about the physical quantity. Now we are going to see how many types of physical quantities we have. There are two types of physical quantity. One is fundamental. So let's see. The types of physical quantity. We have two types of physical quantities. First one is fundamental and the second one is derived. What is the basic difference between the fundamental quantity and the derived quantity? We have to know here. The basic difference is that just first study about the fundamental quantity. Fundamental physical quantities are those physical quantity which are independent from each other. Actually, fundamental quantities are just set of physical quantity, and they are independent from each other, means using any number of fundamental physical quantity, you cannot derive the set any fundamental quantity which is in the same set. For example, just understand. Let's I am taking means right now just I am taking a set of fundamental quantity by my own choice. You can also take that. The first one I am taking is mass, length and density. Actually I am taking these three as fundamental quantities. This is mass, length and density. Actually density is not fundamental quantity, as we know that we are aware about the SI unit or SI system, in which you have mass, length and you say time or temperature, current. But just we are just studying here the how the fundamental quantities are formed and how we have decided that mass, length and time, temperature, current, amount of substance and luminous intensity should be in fundamental category. So this is the basis. You can take actually internationally we have taken this seven quantities as fundamental, but you can derive your own fundamental quantity. So I am just assuming that, let's suppose mass, length and density I have taken as fundamental quantity. Can I take this? First question is that, can I take this as fundamental quantities? So let's see. First point is that those physical quantities which do not depend upon any other quantity are defined as fundamental quantity. So can here you can write density. Let's see this one, density. Let's write density as mass by volume. Okay, this is density, and we can also write this as mass by length to the power q. That means, let's see here, density can be derived using mass, length. That means we cannot take this as set of fundamental quantities because okay, so we cannot take density, mass and length as fundamental quantities because we can derive this density using mass and length. So mass, length and density cannot be taken as fundamental quantity. Can we take another? I am taking another example, is mass, length and velocity. Can we take mass, length and velocity as fundamental now? Now we can take. Just see, you cannot derive. If you want to derive velocity, velocity is displacement by time, or you can say length by time. You don't have time here. That means velocity can never be derived using mass and length. Means all three quantities are independent from each other and they are not derived using each other. That means mass, length and velocity can be taken as fundamental quantities. So this is the basic property of the fundamental quantities. Let's see, we have some another example. Let's see this one. Just see first, and after that I am going to discuss this. Just try to solve this. Okay, okay, I am blocking your way. Just see, I need the answer. Okay, I am waiting for your answer. Tell me that 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. Just tell me the number which one can be taken as fundamental quantity, the set of physical quantity. I am waiting for the response. Okay, 2, 1. Okay, my audio is very low. Am I audible to you now? we will discuss about the DPP. Actually, I didn't study your chat, so we'll discuss about this DPP in next class. Okay. I got only one answer to only two. Length, mass, and velocity. I have taken that exam. What about force, time, and work? Can we take as fundamental quantity? Tell me your okay. I need to increase the audio. Okay, just is it clear now, Charan? Let's see. Now I am discussing the first one. We have seen that it's an example above that we cannot take mass, length, and density as fundamental quantities because they are related to each other. Now, the next, length, mass, and velocity. That means we cannot take this as fundamental. Length, mass, and velocity can be taken as fundamental. So 2 is right. What about the 3? So 3. Just a minute. Okay, we are just doing some settings. Just a minute.
Hello.
Up. Is it audible now? Up. Okay. Let's see. Okay, is it audible now, Charan? Is it audible? Okay, let's see. The third one, that is force, time, and work. Now try to relate it. You know the formula of work. Okay, we have seen the work. Just let me change the pen. Okay, let's see. So work is equal to, this is force into, you say it, displacement. Now to derive work we need force, so you have this force here, and the second term is displacement. Do we have displacement here? We don't have displacement, we have time. That means they are not dependent on each other, they are independent. That means this set can be taken as fundamental. Now I am coming to fourth. Just see, here we have this length. That means work can be derived using force and length. That means we cannot take force, length and work as fundamental quantity. Now you know that. What about the fourth one? I need the answer. I have discussed 1, 2, 3 and 4. Now tell me about the fourth one. It's for all of you. What's the, can I take it as fundamental or not? I need the answer. I'm waiting for your answer now. What about the fifth one? No. Okay. Yeah, this is the correct answer. We cannot take force, pressure and length as fundamental because this pressure, just see, this pressure can be written as force divided by area, and this is force by area is length square. So using force and length we can derive this pressure. So we cannot take force, pressure and length as fundamental. I think it's clear now. Do you have any doubt? If you have any doubt, just tell me. Now, this is the second type of physical quantity. Yes, Sharon, tell me about your doubt. Okay. Okay, let's start with the derived quantities. What is derived quantity? Let's see. So actually basically derived physical quantities are derived means using fundamental physical quantity. They are completely dependent on choice of fundamental quantity we choose, and we have so that's our the derived quantities. You know this is a name. That means it is derived from fundamental quantity. You can take many, for example, you know, is speed is distance by time, density is mass by volume. If you want to derive force, we can derive force. Force is mass into acceleration, or acceleration can be written as length by time square. So it's derived using the fundamental quantity. Every physical quantity, the derived physical quantity is dependent on fundamental quantity. Now, so the question comes, if we start assuming fundamental quantity by own, let's, in certain reason we are taking mass, length and velocity as fundamental quantity. That means can we derive for example, I choose mass, length and velocity as fundamentally. Somebody choose as mass, time and length as fundamental. Some choose length, time, temperature as fundamental. So we cannot come to a common ground. So that is SI, means International System of Unit. That is a internationally means every country assume that these are the fundamental quantities, that are 7 fundamental quantity which are mass, length, time, temperature, electric current, luminous intensity, amount of substance, and these are also called base quantities. There is another name for fundamental quantities. These are also called base quantity. So why we are using 7? In earlier examples I have shown you that I have taken only mass, velocity, time, or mass, length and time. Now I am giving you the 7 fundamental quantities. The basis is that using mass, length and time we can derive many physical quantity, but we cannot derive the quantities which are dependent on temperature. Okay, without electric current we cannot define or derive the terms we use, in which we use charge. In Coulomb's law there is a effect of charge, so we cannot derive even the luminous intensity. So we need this 7. If in future if we discover something new and we need more physical quantity to derive that physical quantity, there may be another 8 one. So right now every physical quantity we have can be derived using these 7 physical quantities. So that's why we are taking this as a fundamental quantities. Okay, now so these fundamental quantities, so we have another example. Just do it. I need this answer. I am just waiting for the answer. Which one is the correct answer? I need the answer. I didn't get the answer. Which one is the correct? 1, 2, 3, 4. Just tell me. 4. I got one answer, 4. We have to find which of the following sets cannot enter into list of fundamental quantities. Tell me. Chan, why you are writing again and again? There is no need of that. Tell me, I got only one answer till now. Yes, I am reading all the comments actually. When I see downward, I am just seeing all the comments. So comment here, okay? Whatever doubt you have, just place in the comment box. I'll reply, okay? Just see, you have to cannot. That means there should be means you can derive them. For example, just take length, mass and time. That means they are not set of fundamental quantity. So just see. No, actually, just see Ananti, you are just having a doubt. Just see. The first, initially I have told you that physical quantities are of this type, okay? So fundamental quantities are, just see, these are the fundamental quantities. Just see, in length you have distance, displacement, everything you have. So these are set of fundamental quantities. They are not saying asking about the scalar or vector quantity. In other are completely a scalar. In length you can have vector also. So that's did you get your answer, Ananti? Okay, let's see the answer. So, we have to just find uh, which set cannot be fundamental quantities. So, first, length, mass, and velocity can be, because they are not dependent on each other. The second one, length, time, and velocity, they are dependent on each other. Just see, you know that velocity is equal to length by time. Okay, so there. Now, mass, time, and velocity, they are not dependent. You don't have any formula that can occupy all these three quantities. Length, time, and mass, they can also be taken as fundamental quantities. That means the second one is true. What are you doing, everyone? You are saying 3, 4, that means there is some do you have any doubt now? Just ask here. After that I'll move ahead. Okay, because you all have not given the correct answer. Did you get this? Okay. I am moving to the next topic, units. Now see, every physical quantity is represented in form of some standard reference. Okay, they are related with some standard reference. So the unit of a physical quantity is the reference standard used to measure it. Every physical quantity has some unit that just relate that physical quantity with the units. Okay, you need the fundamental quantities. So just a minute, I am going back. Let's see. Actually, I have told you that fundamental quantities are independent from each other. They cannot be related. If you have this three set of fundamental quantity like mass, I am taking, these are not fundamental quantity. I am taking an example that mass and length and density, can they be taken as fundamental quantity? So let's see. Density can be derived using mass by volume or mass by length cube. It means density is dependent on mass and length. That means you cannot take density as fundamental quantity. Okay. Similarly, just see here in the example we have seen, you have four options: length, mass, and velocity. If you derive this if you want to derive velocity, so to derive velocity you require suppose length, that is displacement is length, you require length by time. This means you have for velocity you have mass by length. So you have length here. Just see. You have length here. but we don't have time here. So length, mass and velocity, they are independent from each other, and they can not be derived using this sets. So that means they can be taken as fundamental quantity. But in the second case, just see here, in the second case, velocity can be written as, this formula I have written here. Length by time, you have length, you have time. So velocity can be derived using length and time. That means velocity means length, time and velocity can never be taken as fundamental quantity, and we have to find that can not be taken. That means the second is correct answer. Okay. Now I am moving ahead, means I am just moving to unit. Now let's see units. What is units? So every physical quantity is represented in actually with some reference. Okay, that reference you can say means the unit of a physical quantity is the reference standard used to measure it. Okay, every physical quantity has some unit. To measure physical quantity, a definite magnitude of quantity is taken as a standard, and the name given to this standard is called unit. For example, just take length. So we have given a unit meter to length. If you take mass, we have given a unit kg. So every physical quantity is represented in terms of a in terms of a unit. And after measurement, every physical quantity is written like this. That is, measurement is equal to n. N gives you the how many times is of the standard or the reference we have taken. For example, you have 2 meter. Okay, this is your reference. Meter gives you the physical quantity is length. Okay, and it gives you, it is 2 times of reference, and the reference is meter. That's how we measure every physical quantity. So let's see. In the same way, unit is of 2 type because the fundamental or the physical quantity, the physical quantities are of 2 types. So we have fundamental units and we have derived units. Fundamental units are the unit which are taken for the fundamental quantities. For example, unit of mass, length and time. So we have 7 fundamental quantities. So the units of that fundamental quantities are known as fundamental units, and the derived physical quantity are derived using the units of fundamental quantities. Okay, so it's similar to the fundamental quantity and derived physical quantity. So actually I'll upload that PPT to your I will upload that PPT to our portal, so don't worry about if you missed to write anything, don't worry about that. Okay, let's see. The next point is classification of unit systems. Okay, so what is classification of unit system? We have four, actually these are the CGS system. You know that the second one is FPS, third one is MKS, and the fourth one is SI system. And these are actually, these three are old systems that we have discarded, or actually we don't use for scientific calculations. But we sometimes we represent actually to make the problems difficult, or to show that actually in questions some quantities are written in form of CGS units. So in calculation you have to convert into SI system, so that that means in questions they check that can you convert units or not. So that's why you need to know the what are the um, units we take in CGS system, and what are the fundamental quantities we take in that system. So let's see the basic units of systems. Let's see this one. We have 7 physical quantities as SI. So in SI you have unit for all 7. So why it's like that? Because we have 7 fundamental quantity. But in CGS, FPS and MKS you see you have only 3 units. That's why in these systems we had only 3 fundamental quantities. That means mass, length and time, all 3 are. So initially why it's like that? We need to understand this. Initially these are old system of units. You can understand in this way that initially before the invention of electricity, or the charge, or the interaction of charge, we don't have any information. We didn't have any information about charge or the electric current. So how can we give electric current a unit, or can take it as a fundamental quantity, as we don't know about it? Even we in early days we didn't know about the temperature of any physical quantity, and the luminous intensity and amount of substance. So as we discovered these physical quantities, we needed some units to derive the physical quantities related to temperature, electric current. For example, using electric current, we defined the unit of charge, the unit of magnetic dipole moment, the electric dipole moment, everything we define using this unit, the unit of electric current, or using electric current. Let's see. So that's why in these systems, in CGS, FPS and MKS, we have only 3 fundamental quantities and 3 units. So in CGS, I will discuss SI after discussing these 3. So let's see, in CGS, that is C for centimeter, you can say. It's this C, the first letter C is for centimeter, G for gram, and S for this second. That is the meaning of CGS system. FPS, F for foot, P for pound, and S for second. In MKS, M for meter, K for kilogram, and S for second. Everything has a meaning. Okay. Now, in SI, actually, this system we use these days, and internationally it is recognized. For mass, we use kg instead of gram, pound. Actually, you will say it's the extension of MKS system. You have kilogram, meter, and second. Same in case of MKS system. And after that, you have we have added 4 more physical quantities. Okay. So let's see, the unit of temperature we take as Kelvin, it's Kelvin, okay. Current we take ampere, candela we is the unit of luminous intensity. Amount of substance, the unit of amount of substance is mole. So when do we take SI system? Actually we use all the time SI system. Okay, we are just studying about all the systems, but always we do calculation in SI system. Okay, Charan? Now, let's move to supplementary units. So we have two more supplementary units in set of fundamental physical quantities. These are radian. Radian is actually used for planar angles. So how we calculate planar angle? Let's see. If you have plane, and this is your arc length. This arc length is L, this is radius R, and this is theta. So we say angle theta is arc length divided by radius, okay, and theta is equal to L by R. This is the formula, means 1 radian is the angle subtended by an arc equal to the radius. That means when this arc length becomes R, theta becomes 1. I mean, when did, actually I do not remember the date. I think it's 1891 something. I'm not sure, you have to see the dates, okay. In approx, I think in 1891 we had a conference on system of measurement and unit. We have a international system, it's a community, international community in 1891. I'm not sure, but you have to see that, okay. It's a date, how can I everyone remember that, okay. And you are very expert in searching all the things. Just type and search that, okay. Let's see. Do you have more doubt? Now, we have the second asteradian. Actually, asteradian is used for solid angle. Actually, this asteradian is used for the name of physical quantity is solid angle. Okay. I got information. Okay, nanotech. Actually, we have a question, a tuning fork of frequency 200 hertz is sounded. So it's a question of wave, but I am giving you the answer. So just understand. The number of beats per second is 5. By putting wax on A, the number of beats increases to 8. The frequency of fork B. This is irrelevant to this question here, the topic we are studying, but I am giving you the answer. A tuning fork A of frequency, we have a tuning fork A whose frequency is, suppose it's A, 200 hertz we have given. Okay. And we have another B, okay. So B, the beats is the difference of frequency. So B may have, as we are getting 5 beats, that means it may be 205 hertz or it may be 195. It may be less. We don't know about which one has more. So in both the cases you will get 5 beats by putting some wax on A. Actually we put wax on A. The number of beats increases to 8, the frequency of B. Just see, when you put wax, the prongs of the, you can say this prongs of A gets heavy. As a result, its frequency decreases. So it will decrease more than 200. Okay, and if it is decreasing and you are getting 8, okay, you are getting 8 beats, just compare with this. If it would have been 195, the frequency of B, then the beats will decrease. If the frequency of A decreases than 200, your beats will decrease. But if it's increasing, okay, if it is increasing, that means it's not 195. Just see, it's 205. So if it's decreased, like it becomes 195, 199, the beats is 6. It becomes this becomes 198, the beat is 7. When it becomes 197, the beat is 8. That means the frequency of B is 205 hertz. Now, okay, student. Now I won't discuss the other questions. Okay. Now let's see. Let's see. We have this solid angle. Solid angle means you must have seen a birthday cap or the cone which has area. It's a convex type area. This area we are it's a convex area, and area, if we have area, is equal to capital A, and this is radius r. This angle is known as solid angle. Okay, so this solid angle we represent as omega. So solid angle omega is equal to A by r square. This is how we represent as how we represent the solid angle. Now see, the definition we have written here. It is defined as the solid angle subtended at the center of a sphere by an area of its surface is equal to the square of radius of a sphere. Actually, when this area becomes r square, this one becomes r square, we will get steradian. Okay, so the solid angle becomes 1 steradian. Okay, it is similar to the radian. So these are two supplementary units. Okay, we have some SI prefixes. So let's see what are SI prefixes. So the first, actually, let's we take 10 or 1 as a reference. This one, let's see, your power is increasing. It starts from 1 and goes to 18, and here the power is in negative. So that means it's a smaller prefixes, or let's see. Let's see what are the prefixes we have. In the first one, when it's 10, we say deca. Okay, like decameter you can use. When you have 10 square means 100, we say it hecto, like hectometer. When you have 10 to the power 3, it's kilo, so like kilometer. It's 10 to the power 6, we say it mega, that is megameter. It's 10 to the power 9, we say it giga, like gigameter. When it's 10 to the power 12, it's tera, or we say it terameter. When it's 10 to the power 15, it's peta, or we say it petameter. When it's 10 to the power 18, we say it exa. Okay. Now, so these are prefixes we have. Now, let's see the lower powers, like when the power is 10 to the power minus 1. Okay. So when it's 10 to the power minus 1, we say deci, like decimeter. When it's 10 to the power minus 2, we say it's centimeter or centi actually. And when it is 10 to the power minus 3, it's a milli or millimeter. 10 to the power minus 6, it's micro or micrometer. When it's 10 to the power minus 9, it's nano or nanometer. When it's 10 to the power minus 12, it's pico. 10 to the power minus 15, it's femto. 10 to the power minus 18, it's atto. Okay. So these are the prefixes we use, and you just have to remember up to actually 10 to the power minus 15, it's okay. So these prefixes you have to remember. Now, this is all we have to study in units. Now we are moving to dimension and dimensional analysis. Do we have any doubt? Do you have any doubt? Just tell me. After that, I am starting this dimension and dimensional formula. It's very important topic. Okay. Now I didn't get any response, so I am starting this dimension. So dimension is, I think, it's more important than the units, but both has own importance. So let's start with dimensions and dimensional formula. What is dimension? The first point comes in our mind. What is dimension? Okay. So dimension, every physical quantity we have seen that every derived physical quantity is represented in terms of fundamental quantities. That means, and you must have seen, just see here, if you write density, we have already used this density. So if you write density, density is written as mass by volume, or there is another term we write as mass by length to the power 3. So we write it as mass into length to the power minus 3. Okay, let's see what is the meaning of this. We have written this density in terms of mass and length, and that is, you say it has, the density has power 1 in mass and power, we say it exponent minus 3 in terms of length. So the powers of the fundamental quantity, so the formula of dimension or dimensional, you can say definition of dimension is, it is the powers or the exponent raised to the fundamental quantity are known as dimension of the physical quantity. So see, all the physical quantities of interest can be derived from the base quantity, we know that, and the power or exponent we have written here of base quantities that enters into the expression of a physical quantity is called the dimension of physical quantity. That means this power, so we can write here dimension of density is you just write, we have two dimensions, so dimensions of density are 1 in mass and -3 in length. Okay, so we have this 1 power of mass and -3 power of length represents, actually these are dimensions of density in terms of mass and in terms of length. So we have some comments, let me see. Okay, just take another example. We have seen density. Just write acceleration. If you want to write the dimension of acceleration, just I am writing acceleration as, you can write length, the displacement length by, you write velocity by time, or just write velocity by time. Okay, after that I'll convert. Write velocity by time, and velocity can be written as length by time. So it becomes length by time square. So acceleration is equal to length into time to the power -2. So what I write, acceleration has dimensions one in length and -2 in time. Okay, so this is how we represent dimension of any physical quantity. So here we have another example, force. How we write? So force can be written as mass and acceleration. Just tell me, do you have any doubt? Okay, if anybody has any doubt, just tell me. And let's see, the next one is, we have this mass into acceleration can be written as acceleration, we have seen that is length into time to the power -2. Okay, and we can write, okay, so the dimensions of force are 1 in mass, 1 in length, and -2 in time. Okay, so actually we write every fundamental quantity as actually in short form. Okay, so because if you all the time if you write mass, length and time, so it takes time, so we just write in short form mass as capital M, length as capital L, time as capital T, temperature as theta, or sometimes we use capital K also, that is Kelvin. So theta is theta or Kelvin we use. Now the next is amount of substance, or you can write current electricity, or current we write as I, or sometimes it is also written as A. Amount of substance as mole. Luminous intensity as CD, and yeah, we have this. Okay, we have all 7 physical quantities, so we don't have any more physical quantities now. Okay, so let's see. So that's why we write force as mass as m, L to the power minus 2 and T to the power minus 3, and we also write in this formula as a square bracket m L T to the power minus 2. So whenever you just put any physical quantity in a square bracket, so its symbol actually, it represents that force, the dimension of force. It says not force, it says that we are writing the dimension of force. And m is for mass, so we can write the force has dimension 1 in mass, 1 in length, and minus 2 in time. So this is the dimension of force, and this expression, the expression I have written here, the force is equal to m L T to the power minus 2 is known as dimensional formula of the physical quantity force. Okay, so such an expression for a physical quantity in terms of base quantity is called dimensional formula. Okay, let's see. Let's derive some dimensional formula of physical quantity that we are going to derive here and how we represent. So I'm starting with first one as velocity. Okay, so I have not written here because we have to derive with here I am driving. Okay, so just see. So velocity is written as displacement by time. Let's see, it's displacement by time. Okay, so the dimension of velocity is dimension of displacement. So displacement is length, so it's length divided by time is t. So we can write it as dimension of velocity as L into t to the power minus 1. One more thing, actually you can also, if you want to write, it can also be written as m to the power 0, L to the power minus 1, and like this. Actually, if we have to write like this, we should also write all the fundamental quantities power as 0. So there is no need of writing this way. Whenever you have this formula, just understand that the dimension in other physical quantity, other fundamental quantity, the dimensions of other fundamental quantities is 0. For example, mass has 0 in mass, 0 in current, 0 in mole, 0 in candela. Every dimensions are actually 0. Let's see the another one. We have acceleration. Let's derive acceleration. So acceleration A is written as velocity by time. So velocity, let's find this dimension of acceleration. So dimension of acceleration is dimension of velocity, and dimension of velocity we have calculated here. This is the dimension of velocity. This is L t to the power minus 1 divided by t. So this is L t to the power minus 2. This is the dimension of acceleration. Okay, now let's see. Another one, the dimension of force I am finding. Actually, we have seen the dimension of force above. So I'm not finding dimension of force, just find dimension of pressure. And work, let's start with work. Dimension of work. Okay, so work is force into displacement. Okay, so force into displacement means dimension of work can be written as dimension of force into dimension of displacement. Let's see. So dimension of force we have, you have seen it's ml t to the power minus 2. Dimensional formula of force and displacement is L. So dimension of work is ml 2 t to the power, this right, ml 2 t to the power minus 2. Okay, this is the dimensional formula of work. Power, okay, I'll find that, don't worry. We have a domain of power, so let's find the dimensional formula of power. So the fourth one is the dimensional formula of power. So power is force into velocity. This is how it's defined. So the dimension from formula of power is dimensional formula of force into velocity. So you can also write directly LT minus 1 or just write first velocity. Okay, so let's see. So this is force is ml t to the power minus 2 and the velocity is lt to the power minus 1. So dimensional formula of power becomes is equal to m l to the power 2 t to the power minus 3. Okay, now I am getting the answers. Let's see the dimensional formula of this. We have calculated this velocity, acceleration, work, power, then it's 5, then it's pressure. So pressure is force by area. Okay, so dimensional formula of pressure is equal to okay, so the dimensional formula of pressure is dimensional formula of force by dimensional formula of area. So dimensional formula of force is ml t to the power minus 2 by area is L to the power 2 is equal to m L to the power minus 1 t to the power minus 2. Okay, this is the dimensional formula of pressure. Let's see. Sixth one. Tell me which quantity you want to find. Let's momentum, or we say it a linear momentum. Okay. Okay. So we have this momentum. So momentum is equal to mass into velocity we have. Okay, so let's find this mass into velocity, uh, dimension of momentum. Is equal to dimension of mass is m, dimension of velocity is L t to the power minus 1 . Let's see, just a minute. Okay. So dimension of momentum is equal to mass. I can write is as ml t to the power minus 1. Okay. Any more choice do you all have? Let's see. Now, it's enough, I think. If you want to find more, we can find that one. If you okay, then I am starting the another one, means dimensions of, we can write dimensions of angular physical quantities. Physical quantities energy is work, actually, Charan. Work, uh, the work and energy both have same dimensions. Okay. Let's see. I am finding some other physical angular physical quantities. This one is, first one is angular displacement. We say angular displacement means theta. So theta, is defined as arc length by radius. So we can find dimension of theta is equal to dimension of arc length divided by dimension of radius, which is equal to arc length has dimension L and radius has dimension L. That means it's 1, or we say it m0, L0 and T0. So this type of physical quantity which has no dimensions actually, which have 0 in length, 0 in mass, 0 in every fundamental quantities, it doesn't have any dimension. We say it dimensionless. And we have seen one more important point here, that you are writing arc length by radius. Both are length. So one point I can write here as a note, that it's a note that same type of physical quantity physical quantities, you can say, have same dimension. We have seen here, you know that the dimension of arc length means it's a length. For example, you can say dimension of length is equal to dimension of, you can write distance, it's also a type of length. You write as displacement, you write as arc length, you can write as radius, you can write as diameter, you can write as perimeter. Okay, all are, for example, you can write dimension of energy, it's the first example, as gravitational potential, and or you can write as gravitational potential energy, is equal to dimension of heat. Heat is a form of energy. You can write as electrical energy. So it doesn't mean, it means it doesn't depend on the type of physical quantity. If they actually, okay, just let me see, we have a doubt. Actually, joule is the unit of energy. Okay, it's different. What exists? Just tell me. Do they exist? What are you trying to say? Just tell me. The second point we have angular displacement, or sorry, angular velocity. We have angular displacement earlier. So angular velocity has formula is theta by time, or angular displacement by time. So I can write dimension of angular velocity is equal to, yes, there are so many type of the physical constants I have shown you, just like dimension of, for example, I am showing you dimension of mu, refractive index, sorry, dimension of, refractive index, Ri, friction coefficient. There are so many type of physical quantities which have which are dimensionless. Okay, and you have seen that the physical quantity which are ratio of some physical quantity, all are dimensionless. Just see here, the dimension of theta by dimension of time, so it's 1, dimensionless quantity has value 1 is equal to time, so I can write as t to the power minus 1. The third one is angular acceleration. Alpha, we represent as alpha. So alpha is angular velocity by time, you can write, and dimension of alpha is angular velocity has dimension t to the power minus 1, and this is t, so that this is equal to t to the power minus 2. So actually they must be dependent on other type of means fundamental quantities. Like if they don't depend on mass, length and time, Ananti has doubt, that means they must be dependent on current, amount of substance, luminous intensity. They must be dependent on some type of other fundamental quantity. Okay. Okay. So I think we should over this class now, and in the next class I will start from this angular acceleration. Okay, and I'm ending this class. If you have any doubt, just tell me that. Okay. Okay, everyone, do you have any doubt? Okay, then if you have any doubt, we can discuss in the next class. Okay, then bye bye, take care all of you.